Good morning, dear students. Last class we have discussed the XOR problem and how this can be overcome by realizing or by overcoming this XOR problem or by realizing it with the help of a multi-layer neural network. We have seen that in the previous class, and basically XOR problem is a linearly non-separable pattern classification. So linearly non-separable pattern classification can be realized using multi-layer neural network, and training of this multi-layer neural network is usually done with the help of a special algorithm called as error backpropagation training algorithm. There are other algorithms also. R category training algorithm is available, but anyhow, the best method of realizing a multi-layer but the best method of training a multi-layer neural network is error backpropagation training algorithm. So before going to see what is error backpropagation training algorithm, let me have a brief recap of what is a multi-layer neural network. So see here, so this is a multi-layer neural network. As the word indicates, multi-layer, you have more than one layer of neurons connected. Okay, so that means any neural network will have a set of inputs and the outputs. So see here, so this is the set of the inputs, that is nothing but the input layer of source nodes, and these are the outputs. This is the output layer, and in between the input nodes and the output layer you have another layer of neurons, which you call it as a hidden layer. Since this is available in between the input nodes and the output layer, this layer of neurons is called as a hidden layer of neurons. Okay, right? So you can see this network is a fully connected network. What is a fully connected network? Each and every node of the input is connected to each and every neuron of the hidden layer. That means, let me say this is node number 1, okay, and this is neuron number 1, 2, 3, 4, and so on. Node number, input nodes 1, 2, 3, 4, and so on. Okay, so node number 1 is connected to the first neuron of the hidden layer, likewise the second neuron, the third, the fourth. Likewise, all the input nodes are connected to each and every neuron of the hidden layer. Likewise, the output of the hidden layer becomes the input to the output layer of neurons. Here you can see that all the output layer of neurons are connected, fully connected to the hidden layer of neurons. Is it not? So see here, this is connected to the output layer neuron 1, the output layer neuron 2. Likewise, this is connected to this and this one connected to this and this, and so on. So this is basically a fully connected network. Okay, so now how do you train a neural network? Basically, let us forget about this multi-layer neural network. How do you train a neural network? So the procedure goes like this. Initially, you need to provide the inputs to the to the network. The output will be calculated, that you call as the actual output. That output will be compared with the desired value. So there will be some error. If the error is 0, there is no need to update the interconnection weights. But if there is some error, based on the error, you need to update the neural network using the generalized learning rule. Okay, so that is nothing but the new weight is equal to old weight plus the change in weight, that is nothing but delta W, if you remember. Okay, so that we have discussed in the previous one of the previous sessions. Okay, so if you consider this case, this is a multi-layer neural network. If you would like to train this neural network, okay, using a supervised learning rule, that is, you should know the desired output. So I can update the interconnection weights between the hidden layer and the output layer as I know the desired output. Let me make it clear to you once again. So if I know the desired output, the actual output will be compared with the desired values. So based on that error, the interconnection weights will be updated. If you consider the hidden layer desired outputs will not be known to you. So if I don't know the desired layer, if I don't know the hidden layer desired outputs, so what I need to do? I need to go with a new procedure, because since I don't know the desired output of this hidden layer, I cannot update the interconnection weights between the input nodes and the hidden layer. Is it not? So we have a special learning algorithm or a special training algorithm, which you call it as error backpropagation training algorithm. So this particular error backpropagation training algorithm is a very popular algorithm, and this is also very important for your examinations. Okay, so let us now try to discuss what is error backpropagation training algorithm. So before going to discuss the error backpropagation training algorithm, once again we will see a continuous multi-layer neural network to understand you the terminology. Okay, how do you represent the input nodes, what are the interconnection weights of between the input nodes and the hidden layer, between the hidden layer and the output layer, how do you designate or how do you indicate the output terms and all those things to make you understand in the algorithm. Okay, let me consider this diagram. These are all, here you can see, these are all the neurons. So these are represented not in a circular shape, these are represented in this shape, indicating that these are continuous. The activation function used is a continuous activation function. Okay, the activation function is used as a continuous activation function. Okay, so that is the reason why the neurons are indicated in this manner. Okay, and before trying to understand this, if you remember the XOR problem there, when we have represented the or when we have realized the XOR problem, when we have drawn the neural network, okay, the input layer, the input nodes, the layer of input nodes, okay, there you can see that apart from the two inputs x1 and x2, we have another input that is -1. If you consider the hidden layer also, okay, apart from the two outputs, that is O1 and O2 of that hidden layer, you have another element which is -1. Okay, so basically to train a multi-layer neural network, you usually augment the given input patterns. Augmenting is nothing but increasing. Okay, so increasing the size of the given input pattern by another element by which is nothing but -1. Okay, so here you can see this is a multi-layer neural network, the inputs are represented by Z1, Z2, Z3, Z4 and so on up to Zi. Okay, Z1, Z2, Z3, Z4 and so on up to Zi, Z small I and Zi minus 1, and Zith element, that is the last element, is minus 1. See here, this is a fixed input. You have augmented the given input vector by minus 1. So this is a fixed input. See here, you can see here, fixed input, that is minus 1. Okay, right? So if this is ith element, obviously the left out elements in the input nodes will be I minus 1. So that is the reason why it's indicated like Z1, Z2, Z3 and Z small I and so on up to Z capital I minus 1 to Zi. Okay, Zi is nothing but minus 1. So Z indicates the input of the neural network. Okay, the term Z indicates the input to the neural network. Now this is the hidden layer. Okay, now these are the interconnection weights between the hidden layer and the input nodes. They are represented as V. The interconnection weights are represented by V. So this interconnection weight is represented by V1, 1. You know how to represent the notation. Okay, this is V source and destination, V1, 1. So this interconnection is obviously, this is jth element, jth neuron, Vj1. See this, so Vj1. And what is this? J minus 1, no? So this weight will be Vj minus 1, 1. Okay, in the same way, this interconnection weight will be, this is jth element and this is ith element, Vji. Okay, you know how to write these weight vectors, okay, or indicate these weights, V1, 1, V1, 2, V1, 3 and so on up to Vji. Okay, alright, so these are the interconnection weights. So Z indicates the input vector, V indicates the interconnection weight between the input nodes and the hidden layer. Okay, and the next comes the output layer of neurons. You can see that output layer of neurons are connected with the output of the hidden layer, was it not? So the output of this hidden layer are indicated by Y1, Y2, Y3 and so on up to Yj small j and so on up to Yj minus 1, and the last element is Y capital J, which is indicated as minus 1. I already told you, we are augmenting the input vector by minus 1, we are augmenting the output of the hidden layer by minus 1. Okay, right? So obviously if I indicate that this is Yj, jth element, last element is J, Yj, obviously the remaining left out elements in the hidden layer will be J minus 1. Okay, so Y1, Y2, Y3 and so on up to Y small j and so on up to Yj minus 1 and Yj equal to, which is minus 1. These are the outputs of the hidden layer. Sorry. Now these outputs of the hidden layer are connected to the output layer of neurons. So you can see here, this is also a fully connected network. Right, the output of the hidden layer becomes the input to the output layer. That is, this is connected to this neuron, this is connected to this is connected to this and this and this and this and so on. Okay, you can also see that the interconnection weights are represented by W. They are designated as W. Okay, so W indicates the interconnection weights. So this interconnection weight is, this is the first neuron of the output layer, this is the first neuron of the hidden layer. So this interconnection weight is W11. This is the first neuron of the output layer, this is the jth neuron of the hidden layer, so you indicate it as W1j and so on. So Now I indicate all the interconnection weights between the hidden layer and the output layer by W. Okay, W11, W12, W13 and so on up to WKJ, where K indicates the number of the kth neuron in the output layer and the jth neuron in the hidden layer. Okay, and the outputs are indicated by O1, O2, O3 and so on up to OK. So here you can see input layer of nodes, okay, comprised of I number of elements. The hidden layer of neurons comprised of J number of elements, and the output layer of neurons are K in number. Okay, so you got it, all of you. Let me have a brief recap once again. Z indicates the inputs to the neural network. V indicates the weight vector corresponding to the input nodes and the hidden layer. Y indicates the output of the hidden layer. W indicates the interconnection weight between the hidden layers and the output layers, and O indicates the output of the neural network. Okay, suppose with this introduction, let me now proceed to the error backpropagation training algorithm. Okay, now the error backpropagation training algorithm goes like this. In error backpropagation training algorithm, there will be two passes. One is a forward pass and another one is a backward pass. Okay, what do you understand by a forward pass? Forward pass in the sense you are presenting the inputs, okay, you are calculating the output in a forward direction. See that you are presenting the inputs here. Okay, first of all you are calculating the outputs y1, y2, y3 and so on up to yj. Okay, so how do you calculate it? Basically y1 is nothing but okay, z1 into v11 plus z2 into v12 plus z3 into v13 and so on up to zi into v1i and so on up to z j into v1j. Okay, once it is passed through the activation function, here we are using a continuous activation function. Okay, let us consider a unipolar continuous activation function, which is nothing but 1 by 1 plus exponential of minus lambda net. Okay, right, so this is the output of the hidden neuron 1, that is y1. So y1 is now presented as input to this first neuron. Okay, likewise y2 is connected to the first and so on. Okay, so how do you calculate O1? O1 is nothing but the continuous activation function of, that is f of, okay, w11 y1 into w11 plus y2 into w12 y3 into w13 and so on up to yj into w1j. Okay, so I can find out what is O1. Okay, so how I am doing here, I am presenting the inputs, calculating the output in a forward direction. This is what is called as forward pass, which you usually observe in the training of the neural network, calculating the output in a forward direction. Once I calculate the output, what I'll be doing now, I'll be comparing this obtained outputs or the actual outputs with the desired values. Desired values are indicated by D1, D2, D3 and so on up to Dk. Okay, so now the desired outputs minus the actual output gives you the error. Now here comes the second phase of training, that is nothing but propagating the error in a backward direction. That is the reason it is called as error back propagation training algorithm. So whatever the error is obtained, that error is back propagated. Okay, you can understand that error. What is the error here? D1 minus O1, D2 minus O2, D3 minus O3, dk minus ok, dk minus ok. That error is propagated in a backward direction. Okay, in calculating the or in updating the interconnection weights or in calculating the new weights. Okay, what I need to do when I'm training the network, it implies that when I train the network, obviously the interconnection weights need to be updated. How I need to update the interconnection weight using this algorithm? I have to back propagate the error. Whatever the error is obtained, that error is being back propagated. Okay, and accordingly the interconnection weights wkj and the interconnection weights vji are updated. Got it, all of you? Right, once again I'll tell you, error backpropagation training algorithm is executed in two ways. That is, one is forward pass and another one is backward pass. In forward pass, the output is calculated in forward direction, that is presenting the inputs, calculating the output in a forward direction. The backward pass is nothing but once the output is calculated, I know the desired output. The desired output minus the actual output gives you the error. Based on that error is being back propagated, okay, in calculating the interconnection weights W and in updating the interconnection weights W and V. Okay, so this is simply the gist of error backpropagation training algorithm. Okay, right, now we'll go into the algorithm, the steps involved in the algorithm. See here, there are p number of training pairs. What are training pairs? Training pair is nothing but input and the corresponding desired output corresponds to a training pair. Okay, so how do I represent input? Input is represented by Z and output is desired output is represented as D, is it not? So Z1, D1, Z2, D2 and so on up to ZP, DP. That means there are p number of training pairs. For p number of inputs, there are p number of desired outputs. So you have p number of training pairs. That p is represented as capital P. See here, p number of training pairs. Okay, where Zi is I by 1 matrix, Zi is I by 1 matrix, Di, Zi is the inputs, Di is the desired output, that is k by 1. If you recollect, the number of nodes in the output layer is k, the number of nodes in the input is j. Okay, sorry, I, this is I. So Zi is I by 1 and that is nothing but a column matrix. Zi is a column matrix I by 1 and Di is k by 1, which is also a column matrix. I is 1, 2, 3 and so on up to p. Note that the ith component of each Zi is of value minus 1. I told you, no? So ith value, sorry, the ith component of each Zi is nothing but minus 1. So you have augmented the given input vectors since input vectors have been augmented. Okay, so j minus 1 is the size of the hidden layers having outputs y. Okay, so note that the jth component of y is of value minus 1. So the jth component is also minus 1, augmented the hidden layer since hidden layer outputs have also been augmented. So therefore y is y. See how is y? Y is y1, y2, y3 and so on up to yj. That is nothing but j by 1 matrix is represented as j by 1 vector and O is k by 1. O, see here, k number of elements are there, O1, O2, O3 and so on up to OK. So k by 1. Okay, right. So this is the brief introduction to the size of the inputs, output of the hidden layer and the output of the output layer. Now coming to the first step, step number 1 is eta, which is called as the learning rate, is chosen as greater than 0, and error is chosen as Emax. Okay, error Emax is also chosen, maximum value of the error is also chosen. Okay, so since this is a continuous uh, activation function being used, exactly you don't get the 0 error. So what we do, usually we fix the maximum error. Okay, and we'll later on compare the obtained error with this maximum error, and accordingly we take the decision whether to stop the training or not. Okay, so eta is greater than 0 and Emax is chosen. Weights W and V are initialized at small random values, where W is K by J and V is J by I. So see here, W vector, W matrix, weight matrix, W is K by J. Number of elements is K into J. Okay, right? So K by J matrix, and V matrix is J by I matrix. V matrix is weight vector, V is J by I. Okay, right? So we need to initialize Q is equal to 1, P is equal to 1, and error is equal to 0 initially. Let us assume error equal to 0. Okay, now step 2 is training forward pass. Training step starts here. Input is presented and the layer's output is computed. Okay, that is how do I calculate y? Y is equal to function of v into z. So see here, y is equal to function of v into z. Okay, in the same way, O also can be calculated. How do I calculate O? O is nothing but function of W into Y. Okay, O is nothing but function of W transpose into Y. Okay, you have to transpose the weight vectors, otherwise matrix multiplication will not be possible. So W K transpose into Y. So you have calculated the output of the hidden layer as well as the output of the output layer. Okay, right? So that is step number 2. Step number 3 is once I calculate the output OK, we can find out the error using the formula E is equal to half into dk minus OK square plus E. So that you can see here, E equal to half into dk minus OK whole square plus E. Clear, all of you? E is equal to half into dk minus OK whole square plus error. Error is anyhow initially 0. Okay, so E equal to half into dk. So if I consider the first neuron, D1 is the desired output, so D1 minus O1 whole square, okay, plus D2 minus O2 whole square plus D3 minus O3 whole square, and so on. Okay, so the error value is being calculated using the formula E is equal to half into dk minus OK whole square plus E. Okay, now error signal vectors delta O and delta Y of both the layers are computed. So here, till here we have completed the forward pass, that is calculating the output, okay, and finding out the error, that is the forward pass. And the backward pass is you need to find out the error signal vectors delta O and delta Y. Delta O corresponds to the error signal corresponding to the output layer, delta Y corresponds to the error signal corresponding to the hidden layer. So we need to calculate it. Okay, how we need to calculate it? See here, the error signal terms of the output layer in this step are delta OK equal to half into dk minus OK into 1 minus OK square. Okay, how I got this? Okay, we'll see, we'll check it once. Okay, how do we calculate the learning signal? I already told you that we have chosen a continuous activation function, so that is f of net equal to 1 by 1 plus exponential of minus lambda net. Okay, we go with, since this is a continuous perceptron, okay, continuous activation function is being used, okay, right, we need to go with the delta learning rule, okay, right. So delta learning rule is there you need to find out f dashed of net, is it not? Okay, so if you remember the change in weight, delta w is nothing but product of the learning rate multiplied by the learning signal and the input, is it not? Is it not? Okay, so in case of delta learning rule, you have the additional term, that is f dashed of net, okay, f of net equal to 1 by 1 plus exponential of minus lambda net. Since that is a continuous activation function, please check the delta learning rule, okay. Here we go with a generalized delta learning rule, okay, right. So f dashed of net is I have done the first order derivative of this, exponential of minus net by 1 plus exponential of minus net whole square. So this can be written as f of f dashed of net equal to, how I have represented it, see here, 1 plus exponential of minus net whole square is split into 1 by 1 plus exponential of minus net multiplied by, okay, exponential of minus net by 1 plus exponential of minus net. Add and subtract 1 in the numerator of this particular term. 1 plus exponential of minus net minus 1 by 1 plus exponential of minus net. Why I have written it in this way? See here, what is this 1 by 1 plus exponential of minus net, which is nothing but f of net. That is nothing but f of net is nothing but the output. 1 by 1 plus exponential of minus lambda net minus net is nothing but the output. So that is f dashed of net is O into, okay, O multiplied by, okay, 1 minus of, so see here, I can represent it as 1 minus, what is 1 minus of 1 plus exponential of minus net? 1 minus O is nothing but 1 plus exponential of minus net minus 1, is it not? 1 plus exponential of minus net minus 1 by, so I think you can understand this. You multiply it with you divide it with 1 plus exponential of minus net, this term only alone. So this I consider it as one term, 1 plus exponential of minus net by 1 plus exponential of minus net, that is 1 minus 1 by 1 plus exponential of minus net will be left out. So that is 1 minus O, is it not? So f dashed of net is O into 1 minus O, O into 1 minus O. Okay, now what is the learning signal? Learning signal is the error, that is dk minus ok multiplied by f dashed of net, that is nothing but, we are considering, let me see, we are considering the kth element, okay, dk minus ok into 1 minus ok. Got it, all of you? What is the error signal or the learning signal? Delta ok equal to dk minus ok is nothing but the error multiplied by f dashed of net, that is nothing but ok into 1 minus ok. So delta ok equal to, see here, dk minus ok into 1 minus okay. So if we use a activation function 1 by 1 plus exponential of minus lambda net,